Good morning, College Park. This is your amazing host, Nicole Huang and Meredith Wilson. Today we're going to be reporting live from the Daily Show.
This just in, shocking news from the University of Maryland College Park. 3 students in the Civil and Environmental Engineering Department program teamed up with graduate student Gabriela Nino de Guzman to test various materials for active remediation of biowall construction. To be specific, they tested the effectiveness of 3 common biomaterials: mulch and compost, zero-valent iron, and glycerol. Here's how they did it.
Overall, there were 2 parts to this experiment: the acid-base titrations and the fluorescein diacetate hydrolysis assay. Both were used to give us an indication of measurements gauging the biological activity of the biowall materials. Acid-base titrations are a common laboratory procedure that allows scientists to determine carbon dioxide concentrations. The fluorescein diacetate hydrolysis assay is a non-specific assay that directly correlates the amount of fluorescein produced to the total biological activity.
For both phases of the experiment, we needed to collect soil samples. Our group attempted to pick a soil that was representative of the University of Maryland soil. Since we all felt like the engineering building was our home, we were able to obtain soil from close by at the Encircle bus stop. We used a bar and a spoon to loosen and collect 3 jars worth of samples. Back in the laboratory, we then labeled 2 sets of 6 jars. We decided to collect our data on the 3rd and 10th day of incubation. Once all the jars were labeled, they were autoclaved to ensure sterilization, followed by UV radiation for approximately 10 minutes within the fume hood, along with the rest of our materials.
We are now ready to add various combinations of soil, zero-valent irons, glycerol, and mulch and compost.
The jars are then placed in a 30-degree Celsius incubator. After 3 days of incubation, we opened the first set of jars and removed the vacuum tubes of NaOH to stop the gas trapped process.
1 milliliter of 50% BaCl2 solution, as well as a few drops of phenolphthalein, were added into each tube.
Then each vacuum tube was titrated. We used 1 molar of hydrogen chloride as a titrant. Before the titration began, the solution was a light pink color. As the titration continued, the solution became a more hot pink cloudy color, and at the end point, the solution became a cloudy all-white color. At this point, we recorded the exact volume of hydrogen chloride used. To calculate the CO2 trapped in the solution, every milliliter corresponded to every milligram of carbon dioxide in the solution.
To complete the fluorescein diacetate hydrolysis assay, we first had to mix 5 solutions. After putting together all of the solutions, we began the reaction by adding the 1000 microgram per milliliter FDA stock solution to our samples. We capped the tubes, shook them by hand, and then placed them into the 30-degree incubator for 45 minutes. When they were finished, we moved the samples to the fume hood and immediately added 15 milliliters of the chloroform methanol solution to stop the reaction. We replaced the caps and shook them thoroughly by hand before putting them into the centrifuge tubes for another 3 minutes. After they were done, we filtered the supernatant from each sample into a clean, sterilized 50 milliliter Falcon tube. Then we transferred 1 to 2 milliliters of filtered supernatant into a cuvette and used a spectrophotometer to measure the absorbance at 490 nanometers. Both of these experiments allowed us to gauge how much microbial activity there was in our samples. Higher amounts of carbon dioxide represent greater respiration, and thus higher levels of microbial activity. We found that the 3-day incubation period resulted in higher levels of carbon dioxide, possibly because the microbes ran out of substrate to consume in the 10-day time period. In addition, a higher absorbance means greater microbial activity. The enzymes produced by organisms do not retain fluorescein diacetate but actually break it down into fluorescein. Therefore, a more intense yellow indicates a higher concentration of fluorescein. Lots of biological activity means lots of enzymes, and lots of fluorescein produced from the breakdown of fluorescein diacetate. This results in a more intense yellow color and thus higher absorption. We filtered the samples to get the solids out so that there would not be any interference when taking absorbance readings. This is how the fluorescein diacetate hydrolysis assay worked. Evidence suggests that biologically active biowalls can degrade pollutants more quickly and completely than their counterparts that only rely on abiotic degradation. As civil and environmental engineers, it is our primary responsibility to develop systems that protect human health and welfare and minimize the adverse effects of human activities on the environment. Part of being an environmental engineer involves providing safe, palatable, and ample water supplies for the human race. It is even better if we can do so using natural processes that protect the environment.